Yeah, so this is some work that I did with my collaborators here. Mostly I'm going to talk about the tool that we're using to numerically compute the intervals that appear in these types of amplitudes and some of the numerical methods that we're using. So this is the ACAT collaboration who wrote the program that I'll present here today. First, the motivation for looking at these particular amplitudes and to do this numerically, so let me start. So now that the LHC has discovered Higgs-like particles, I think the next important steps are to measure precisely its couplings, which is a procedure that's already well underway. Here we see a combination, but from ATLAS and CMS from run 1, so it's a little old. But they're already beginning to pin down many of the couplings for the Higgs boson, and also to explore in detail the distributions. So when the Higgs is produced in addition to another particle, such as a jet or a Z, it's really important that we explore also these distributions, because beyond standard model particles could appear most clearly in these distributions, and not just by rescaling these couplings. So for this, we need to understand the distributions well. So there are several important Higgs channels in the standard model that are loop-induced, and they're known only at leading order if we include the full top quark mass dependence. Now, why is this important? Well, if we use the Higgs effective field theory, where the mass of the top is taken to infinity, and it's essentially integrated out, it's an approximation. And it tells us that the next leading order that we should expect is quite large, even comparable to the leading order. So we can expect very large corrections when we go beyond leading order 1 loop here. And we can expect these higher orders to significantly modify the distributions. So it's really important that we compute these amplitudes to higher order. Let me talk about a few specific amplitudes that I think are quite interesting. So of course, this Higgs jet production. Why is this important? Well, it contributes to the Higgs TP distribution. And especially, it's important if we have a relatively large TP that's larger or comparable to the mass of the top. It's important that we include this top quark mass, as the top can come on shell, and we can see threshold effects. So it's important to know this diagram. And additionally, at high PT, we can begin to probe inside this loop. So we'll see that the distributions can be modified by heavy beyond standard model particles, and we can see bumps in those distributions. But we'll only really be able to discriminate this from a standard model if we know well what the standard model predicts. We can also think about, for example, Higgs plus Z production. So this is important for the measurement of the Higgs Z coupling. And the gluon-induced channel here is actually formally next to leading order. So you might think this is not really a large correction, don't worry about it. But of course, because of the large gluon luminosity at the LHC, it can actually contribute quite a lot, around 10% at 14 TeV. And as we saw, the next leading order will be a very large correction on top of it. The EFP is visible there. And also double Higgs production, which is sensitive to the Higgs self-coupling, which is not very well constrained by the LHC at the moment. And this is very important for us to understand, because it's a probe of the electroweak symmetry breaking. So in the standard model, this coupling is predicted in terms of very well-known parameters, and that's the Higgs and the Z. And it's important that we measure this and understand exactly what we should expect from this channel, so that we can see whether the standard model is correct. Yeah. So here I list some of the important work that's been done on each of these channels. For example, in Higgs jet production, there are several next to leading order calculations done in the Higgs effective field theory. And there's quite a lot of work moving towards next leading order 2 loop here. So, for example, this paper computes the planar integrals that appear in this, but not the non-planar. And this paper here computes this process in the limit that this internal quark is nearly massless. So, for example, a B quark, something like this, in comparison. Higgs Z, the next leading order Drell-Yan component, has been known for quite some time. And we've also got the next leading order result in the EFT for this by several groups. For double Higgs production, the situation is a little bit different. So last year, we were able to compute numerically the full next leading order result, including the top quark mass. And so obviously the important question for us is, And we do this again with maybe these other guys. And also known is the next leading order differential results for the EFT for this group also last year. So what's the difficulty? Why aren't all these processes just known as smooth already? So let me talk about one traditional method that I know and that we use for double Higgs and tell you why it's sometimes difficult. So these are the steps that we typically follow. You decompose your amplitude into some form factors and you construct projectors. This takes minutes of computer time. It might take a bit more time for humans because you have to think a bit, but once you know what you're doing, a few minutes. Then you generate your Feynman diagrams. This is really seconds, no problem these days. And then we apply the projectors and start to compute the amplitude. Now, very unoptimized code here is going to take a few hours, maybe a few days. If it's really bad and your projectors are huge expressions, then this can happen. But these three steps are really no problem at all. And this is not the holdup. The next thing that you do is you try to reduce the number of intervals that you actually need to compute. So for double Higgs, you have around 10,000 intervals here, maybe a bit more, and they're very interrelated, and they can be reduced to a smaller set of intervals. And this step is extremely difficult. Running on really powerful machines, you can easily expect this to take more than 6 months, maybe even more than a year if you use public production codes. So this is really a bottleneck. Then the reward for managing to get your integral reduction is having to actually compute the remaining integrals, which is also a challenging task if you work analytically. However, numerically, often we can do this in a matter of seconds or hours to compute these integrals, and that's the focus of this course. The next step is then to generate events and compute a differential cross-section. Now, if you manage to do this step analytically, here's where it pays off, because then it's probably only going to take you a few seconds to evaluate this, even if it's very complicated and you have horrible functions in these matching intervals. Numerically, this is where you pay, because this can take hours or even days per phase space point. But it can be overcome, and I'll show you this a little bit later when I talk about the double Higgs calculation. And of course, the open question, as I said, is this viable for the other amplitudes? And the honest answer is, I don't know just yet. Okay, so let me talk more specifically about the algorithm that we're using to compute our intervals. So obviously, there are many different methods. We've had a few already today. And I'm going to focus on the method of sector decomposition, which enables us to compute parameter intervals. So as we've already seen twice today, we Feynman parameterize our interval, and we compute the momentum intervals. And then we obtain a form that looks something like this, where this u and f are just some polynomials in the Feynman parameters. And what we've done here is exchange L momentum integrals, so that is L is the number of loops, the n, where n is the number of propagators, parameter intervals. So we have an interval of this form. And this is where our method differs a little bit from what we were shown earlier. After we integrate out the delta, we're faced with functions of this form. So we have these u and f polynomials with some powers that depend on the dimensional regulation parameter, so x1 here. And these polynomials can contain overlapping singularities, which appear when several of the Feynman parameters go to 0 simultaneously, which corresponds to UV or IR singularities. And sector decomposition is a procedure which maps each of these intervals into intervals of this very similar form, except that these u and f polynomials are slightly different, such that they have a constant term, and then a polynomial that has no constant term. So these u and f, when x's go to 0, go to finite numbers, and the singularity can be read off because it's a power, just an overall power of this parameter. Just to give you an idea of how this works, one way of doing it is to use iterated sector decomposition. So here we have an integral with an overlapping singularity. When x1 and x2 go to 0, this has an overlapping singularity. What you do is you split it into two sectors, one where x1 is greater than x2, and the other where x2 is greater than x1. Then you split up your integral, and then you remap to the hypercube. And when you do this remapping, you can introduce here an x1 so that there's an overall x1 in this bracket, which can be factored out, and it just sits here, multiplying the overall integrand, and the singularities are being factorized. Now, whether this terminates or not depends on the order that you do these decomposition steps when you have more than two parameters. And indeed, sometimes it doesn't terminate. An alternative strategy called geometric sector decomposition always terminates. And both of these strategies are implemented in HiSecDef for code that helps with that. And one of the authors of the text is in the audience. The next step is to expand in epsilon. And the simple case is where we have an overall power, like -1, that's here. We essentially add and subtract g of 0 here, and then we have some poles, which are fine. And then we have a polynomial here that's finite, and this can be numerically integrated. So the important thing is that we can expand analytically in epsilon, and then we can numerically integrate the remaining intervals. And it's different from what we had before. So HiSecDef is a program to numerically evaluate these dimensionally regulated parameter intervals. It's publicly available. You can go to GitHub and you can get it right now and try it out and tell me that it fails on your laptop, and I'll try to fix it, but hopefully it will work. It's a complete rewrite of SecDef, so its predecessor, and it's written in Python and C++ using only open source software. It also supports, for example, contour deformation, which allows you to evaluate intervals in the physical region, arbitrary loops and legs within reason. You pay for this with computation time, and also general parameter intervals, so it's not just restricted to loop intervals. HiSecDef has several new features not present in SecDef. So it allows for an arbitrary number of regulators, so not just epsilon. So if you're not computing loop intervals, but you're computing some more exotic parameter interval, like those that appear in sketch, you can use multiple regulators, that's fine. It also supports very flexible numerators, so contracted Lorentz vectors or inverse propagators or combinations of both of these, that's all fine. It has some improvements over SecDef for handling intervals that don't have a Euclidean region where text decomposition doesn't help you. It also has a symmetry finder for detecting isomorphisms between sectors. So if two of the sectors happen to be the same, it tries to detect that and then saves you on the integration time by just integrating one of them and double the result. It also uses form code optimization to generate efficient code for the numerical integration. And an important feature is that it generates you a C++ library that can be linked to your own program. So it can act kind of like a loop provider for multi-loop problems. Of course, it's not a very fast loop provider because they're numerically integrated, but at least it does the job, so you can check things. But there are also other programs that implement sector decomposition. So there's Fiesta, sector decomposition for C sectors, and I think a private form implementation by these people, which first implemented this geometric sector decomposition. There's publicity for the authors of the other programs. So let me just highlight one feature that's new in HiSecDef. So each sector yields an interval over a unit hypercube. And we can freely relabel the parameters in this polynomial here and get the same interval at the end. So for example, we might have two polynomials like this, and we have the question, are these the same, or to relabeling the different parameters in them? Now for this simple example, probably you can see that they are the same. But for longer polynomials, if you try the most straightforward thing you could, for n variables, you need to try n factorial permutations of these labels. And this can get quite slow for large numbers of parameters. We also want to compare all the sectors, and typically we have many more than two sectors. So we prefer to bring them to a canonical representation. And one idea is to convert these polynomials to graphs and use existing operator tools for graph canonicalization, and then compare these canonical graphs. So how do we do this? We take our polynomial and we look at the exponents. We write these exponents into a matrix. The rows correspond to terms and the columns correspond to different variables. Then we store the coefficients in an additional vector. We convert these matrices to a graph following the algorithm that these two people, McKay and Paterno. So we essentially introduce a vertex for every element of this exponent matrix. Then we introduce a different vertex for each column, a different vertex for each row, and we connect them all. Then we look at what different powers appear in this exponent list, and we introduce different vertices for each of these powers and connect them. And finally, to the coefficient, we introduce different vertex for each different coefficient and connect that to the row. We can convert that to this dreadnought input syntax. We can hash this with dreadnought, and then we can sort and compare the neighbors. Now, you might think this is pretty horrible because the graph isomorphism problem or canonicalization problems also a very hard problem. But this tool is actually pretty efficient and does this quite well. For realistic problems that we have, it solves this for us. But there is an alternative. And actually, it was an algorithm presented here at ACAT in 2011 by Alexei Tapp. And it's again based on this exponent matrix, and it works column by column and then acts recursively. I'm not going to go through the algorithm. It's actually written in some detail in his proceedings. And we initially tried to implement this, but found that it didn't always catch all of the cases. But sitting together with Ben Grohl here at ACAT, I think we've corrected our implementation. And it looks like a promising option. So currently, our unoptimized Python implementation of this seems to be competitive with Redmond. So hopefully I can work a bit more on this, and let's see if we can come up with a better solution than the graph-based one. Okay, so how do you actually get PyTech? You can download it from the GitHub. You can install it with these commands and copy the highlighted lines into your /RC to set your packs up. We have very extensive documentation available online, so every function is documented. There's a getting started guide and so forth. You need Python, NumPy, SymPy, Sync, and a C++11 compiler. And it also relies on this software, which is redistributed. So please cite these authors if you actually use PyTech in your application. Let me give you an example of something that we can attack. This is a massive two-loop box that appears in Higgs Jet. It was computed analytically in this paper last year in a monumental way, and it actually contains elliptic functions. So it's quite a complicated analytic expression to be obtained. It has 6 propagators, and these are the scalar products. And we can convert this propagator and scalar product list into an input card for PyTech. This is how it looks. You import PyTech, and this is just Python. Here, you import PyTech. You say, I want a loop integral from propagators, so I'm not going to construct it from a graph or an adjacency list, which you can also do. But I'm going to really tell you the propagators, loop momenta. Here are my scalar product rules, Mandel-Stans and math symbols. And then you call this loop package function with a name. You pass loop integral of the parameters, and an additional prefactor if you want, which will be multiplied onto your result. And in this case, this is the prefactor that they used in their analytic result. So we multiply it on so you can compare these things. And since they computed in the Euclidean region, we turn off this contour definition option so that we get exactly what they did. You then basically call Python on the run code that I just showed you, and it gives you a library which you can build with the make command. This builds you a C++ library, so this dynamic library. And here is a little Python wrapper that just basically loads the C++ library. It selects to use the Vegas interface, the Vegas integrator from CUDA. It sets the accuracy and the number of evaluations. You specify the phase space point, and then you call it and print the result out. And here you see you get the result and an error about 5 digits, and this took about 3.5 seconds. So not too bad if you just want to check your analytic result, but this is pretty slow and pretty inaccurate. Although note, Vegas is often not the fastest integrator. So for example, the bond performs much better here. And this agrees with the analytic result. Another option that we were looking at is exactly what was presented in the previous course. So again, using quasi-Monte Carlo. So this was an idea of Li, Wang, Yan, and Zhao to use rank-on-shifted lattice rules on sector decomposed functions. And they found very good convergence, so this linear convergence that we heard about in the previous talk. And they used CUDA to implement this on GPUs. And we re-implemented this in OpenCL 1.1 so that it can be run on CPU and GPU. And we use these GPUs to evaluate the entire double Higgs amplitude, so not just the integral, but really substituting it back into the integral and going into the amplitude and going right to a final result, differential cross-section, PP distributions, everything. So that's in our paper that we presented last year. And this gives you some idea of the type of speed up that you're getting from a GPU. So compared to 2 decently powerful CPUs, 1 Tesla GPU is around 4 times faster. Note that we don't currently distribute this with PyTech, and our current plans to re-implement it in CUDA probably, and then hopefully we can sort of provide that with SecDev. So we already heard how these rank-on-shifted lattice rules, where we again pre-compute Z for a fixed number of lattice points, and this is important. We have to decide ahead of time how many points we want and generate a lattice of exactly this size. And it's chosen to minimize the worst case error. And we actually use Dettmillions tool as well to generate our Zs. Then to estimate our error, we don't use the formal error estimate, but we actually just shift this lattice. And this gives us an unbiased estimator of how well we're approximating the function. And this error estimate seems to be relatively reliable for a decent number of shifts, more than 4 shifts. Here is just one sector that I picked out from a sector decomposed loop interval. And this orange line here shows you how Vegas performs. This is the relative error versus the number of function evaluations. So it scales like root 1 over n, exactly as you expect. It has Monte Carlo scaling. If we did adaptations, then this could drop differently. But assume that it's well adapted to the function, then it scales like this. The rank unshifted lattice rule actually sometimes does better than the 1 over n scaling. So I didn't sort of search for a really good example. This was more or less a random sector that I picked out. Some do give you the 1 over n scaling, and we even came across some cases that don't scale quite as well as 1 over n, and we don't fully understand why that is. So see also this paper by Li Wang, Yang, and Zhao, where they also study the performance in sector decomposed functions. The next idea that we had to help us evaluate our entire amplitude, so we're not just interested in one interval, the whole amplitude, was to use stratified sampling. So rather than sampling all of our integrals to the same degree of accuracy, putting the same number of points into every interval, which is hugely wasteful, we actually spent hugely different amounts of time in each interval and put different numbers of points in our lattice rules into each interval. And what we found here is that our non-planar intervals typically took very much longer than the planar interval. So this is the most complicated planar interval, and it took around 11 seconds to compute one phase space point. Here, for example, we pick one particular planar interval which has some tensor in it. And we look at just the finite part, so this is the odd zero, this is just the finite part. After sector decomposition, we have many sectors that contribute here. And what you're seeing here is that we're putting different numbers of points into each individual sector within one order, within one interval. So it's really quite stratified. And we try to take the number of points based on the contribution of this sector to the overall error of the amplitude, but also based on the time that it takes to evaluate points in this sector, so that we try to minimize the time to get to a given accuracy in amplitude. And we do this using Lagrange multipliers. Even after all of this, our amplitude is still horrendously slow to evaluate. So we ask for 3% accuracy on one of the form factors and 5 to 20% accuracy on the subdominant form factor, depending on the ratio of that to the first form factor. And the GPU time per phase space point is in the order of minutes to days. So median 2 hours per phase space point. And this makes me think of a quote by Joey Houston, which is, if a theoretical calculation is done, but it cannot be used by any experimentalist, does it make a sound? So is this of any use because it's so slow? As we kind of demonstrated, we were able to push through enough phase space points already here to make distributions, but that's not really what the experimenters want. They want to be able to call some Monte Carlo program and just get the result magically with Kotlin showers and so forth. And for this, we have to construct a grid in Mandelstam S and T, and we base this grid on all the phase space points that we had, so around 3,007 phase space points. And then we interface this grid to Parhead and MadGraph5 AMC as NLO, and this is presented in our paper from earlier in this year. And you can also take a look at the underlying grid if you want in GitHub. So it uses some interpolation, cloud Hocker interpolation from the SciPy library to actually interpolate between our phase space points, and then the Monte Carlos can ask for whatever phase space point and interpolate to it for them from the existing phase space. So in conclusion, we re-implemented SetDeck. Several new features, including the ability to generate C++ library for evaluating multi-loop intervals, are available. It's publicly available. You can try it out. Please do, and let us know your experience and any issues that you run into. For the double Higgs amplitude, we computed our result numerically, and it's now interfaced to 2 different Kotlin shower programs via this grid. And our ongoing work is to make it also available within Higgs and share that, so the experimenters really have every option they want. And we'd like to make a fully differential and improved combination with the NNLO EFT result, so to sort of re-weight their result so that it's at least next to the big order accurate with the full top mass, and then it has kind of the correction coming from the EFT to hopefully get closer to the true result. and then apply our methods and frameworks to other processes. So thanks for listening.
Comment. How did you speed up with the?
So I showed a diagram here.
Yeah.
So essentially we have the number of cores of the CPU that we're using here, which is 2 Xeon E5 CPUs. And this is the number of the millions of function evaluations we can do per second. So higher is better on this. And if I use all of the cores of both CPUs, I get just maybe 6 million function evaluations per second. And this green dot up here is 1 Tesla GPU. And that's a 4.1 times speed up. So compared to these two decently powerful CPUs using all cores, we get a 4.1 times speed up.
Other questions or comments?
Question. So I just want to clarify the history. So you kindly refer to our work for the dimension. What we implemented in form is just strategy. I feel sometimes people are confused with it, but
so you implemented an iterative strategy, not a geometric set.
Such as the motion implemented in pure Python.
By yourselves,
Okay. Yeah.
but in Python.
In Python. And very very.
Okay, then thank you for this clarification. We also implement in Python, so okay, you beat us for that as well. So.
Other questions or comments? I have one naive question about the contour deformation. In every case, you can find your package find a nice contour to get the answer.
Not in every case. So what can happen is the singularities that appear in the integral can either move. So if we look along the axis of one of the parameters, we can have singularities that we need to say go above this singularity and below this singularity. And those singularities can move together, called a pinch singularity. And then our contour is pinched. And what happens there is the numerics get slower and slower and slower as they move closer together. Another thing that can happen is an endpoint singularity. So in our contour deformation, we start on the real axis, we deform in the imaginary plane, and then we come back to the real axis. If those points move to the ends of the line, so to 0 and 1 in that final parameter, they can pinch our contour against the end. And then again, our numerics get slow. And normally that happens around anomalous thresholds in the integral. So it has kind of physical interpretation when we can't find a contour deformation. But this means, for example, as the tops are going on shell, as we get very close to that threshold, it takes much more time for phase-space point, which is why I said it takes between 80 minutes and 2 days. That's because we're taking a lot longer. Exactly at that threshold, probably our method would not work.
Oh.
Okay, just as a follow-up to that, you cannot somehow isolate the singularity that is associated with the thresholds or physical singularities in some analytic way like you do in initial steps of sector decomposition.
So in the initial steps of sector decomposition, the singularities show up at one endpoint, and we have good control. So it's basically when everything's going to 0, and there's an algorithm that can resolve those types of singularities. Mm-hmm. These types of singularities that require contour deformation can appear as hyperplanes inside the space, and it's not necessarily difficult to find them. So maybe there is a way, but yes, I don't know of a way to do that.